Dr. Pavitra Bharadwaj. I am Associate Professor of Computer Science in the Department of Computer Science, Jesus and Mary College. We were discussing about the CPU scheduling and how the operating systems they aim at maximizing the CPU resource utilization by using the various algorithms, by using the short term schedulers. And we were also talking about the different yardsticks or different criteria that can be used for measuring the utilization of a CPU. So, we had talked about the throughput, we had talked about the waiting time, we had talked about the turnaround time, and we had talked about the response time. So, these are the four main criteria which are used for estimating the utilization of any CPU. Now, the idea is to minimize the response time and to maximize the throughput, right? To minimize the response time, to minimize the waiting time, and to minimize the turnaround time, and to maximize the throughput. But the thing is that instead of going for maximizing and minimizing of the various criteria, the systems they aim at bringing the average down. That is, we want that the average response time of a CPU should be minimum. The average waiting time of the CPU should be minimum. Instead of the the maxima and the minima, we are looking at the averages for the purpose of estimating the utilization of any CPU. So, now keeping these four yardsticks or keeping these four criteria in mind, now we will be looking at the different types of scheduling algorithms which can be used. So, CPU scheduling, when we are saying, so very important aspect of CPU scheduling is the scheduling algorithm, because it is deciding on which particular technique to use, which particular way to use, so that the maximum CPU utilization can be attained, the minimum waiting time can be created, minimum waiting time can be obtained. So, which processes should be arranged, the way the CPU should be allocated to the different processes which are waiting in the ready queue, right. So, therefore, there are many CPU scheduling algorithms which can be studied, but we will be studying a few of those. Like the first one that we study is the most simple algorithm, that is the first come first serve scheduling algorithm, which is very commonly known as FCFS. First come first served is the normal queuing algorithm, that is in which the new process which will come will be added to the tail of the queue, and the CPU will pick the process which is at the head or at the front of the queue. So, this scheme, the process requests the CPU, the first to request will be the first to get, right. So, the implementation policy is also very simple, because it is managed using a first in first out queue. We have already done this first in first out and last in first out. So, here we are going to use the first in first out, that is the normal queue mechanism. So, whenever the process will enter the ready queue, its process control block will be linked or will be added to the tail, and when the CPU is free, so it will be allocated to the process at the head of the queue, as I just said. So, the running processes is then moved from the queue. The process which is terminated, it is removed from the queue. So, all processes are added at the tail and they are removed from the head, they follow this. Now, the negative side is that the waiting time, the average waiting time that we had discussed, that we will not take the maximum or minimum, we take the average waiting time. So, that in the FCFS policy is quite long. Like for example, if we take this process mix where we have three processes, you have P1, P2 and P3, and these have a burst time of 24 milliseconds, 3 milliseconds and then 3 milliseconds. Now, if we assume that they arrive at time 0, so process P1 will be the first in the queue, then P2, then P3. So, then they have to be assigned or they have to be allocated the CPU in this order only. So for showing this, a very common chart which is known as the Gantt chart is used. So in this case we prepare a Gantt chart to show how the processes will get reflected or how the processes will get executed. So if you see here, process P1 starts at time 0, so its waiting time in milliseconds is 0. Process P2 will start only when P1 releases the CPU. So therefore process P2 has a waiting time of 24 milliseconds. Now because it takes 3 seconds to execute, so then after 27 milliseconds only process P3 will start. So therefore the average waiting time in this algorithm will be 0 for P1, 24 for P2, 27 for P3. So the average waiting time is coming to 17 milliseconds, which is quite high. For any process, this waiting time is quite high. So if the processes they arrive in another order, say for example, that is P2, P3 and P1, that is the process P2 comes first in the queue, followed by P3, then P1. So then in this case the waiting times will change. Now the P1 waiting time will be 6 milliseconds, P2's waiting time, because it is first in the queue, so it will be 0, and P3's waiting time will be 3. So now the average waiting time is coming out to be 3 milliseconds. So we understand that how different processes, when they are arranged differently in the queue, their waiting times can drastically change, drastically differ. So therefore this FCFS algorithm, this is a different, and it's it's not a very suitable algorithm, because even in a dynamic situation this can create a lot of chaotic environment in the system, which is also known as the convoy effect. It's very interesting to note that if we have one CPU bound process, okay, and we have multiple IO bound processes, so as the processes flow around the system, the following scenario can result. So what is going to happen, you have one CPU bound process which will get the CPU and it will hold on to the CPU. Now during this time, when the CPU has been assigned to that process, all the other IO bound processes will go for their IO and they will finish their IO. After they finish their IO, they will move into the ready queue and they will keep on waiting for the CPU. Now once the CPU is freed by the CPU bound process, they will keep on waiting and the IO devices will also remain idle. The CPU is occupied but the IO devices are idle. Now eventually after its completion, the CPU bound process will finish the CPU burst and it will go for an IO burst, IO device. Now in this case, the CPU is assigned to the IO bound processes which are again having short CPU bursts. Because they have short CPU bursts, so they will execute very quickly and they will again move to the IO queue. Now at this point the CPU is sitting idle because the processes are waiting for the IO and the CPU bound process is now using the IO. Now CPU bound process, after it completes its IO, it goes back to the ready queue and it is allocated the CPU. Now again the IO processes will end up waiting in the ready queue till the CPU bound process is done. So this effect, that at any given time either the IO or the CPU, one of the things remains idle, right. This is known as the convoy effect, because all the processes, they wait for one big process to get off the CPU. This effect will definitely, it will lower the utilization of both the CPU as well as the devices, and it is possible, it might be possible that if shorter processes were allowed to go first, that is if the shorter processes executed first, then this effect would not have happened. So this FCFS scheduling algorithm is non-preemptive algorithm, that is once the CPU has been allocated to a process, then that process will keep the CPU till it is released by the process. Okay, and when will it release the process? Only in two conditions, that is either it is terminated or this goes for its IO burst. Therefore, this algorithm is not, you know, very favorable algorithm, and it is rather troublesome algorithm, and more so in case of time sharing system. Time sharing system means that, you know, where every process must get a slice of the CPU time. So there every user needs to get a share at regular intervals, but in this case, because of the convoy effect like thing that we saw, that is not going to happen. Therefore, FCFS algorithm is not a very preferred algorithm for use in CPU scheduling. Then the next algorithm that we see is the shortest job first algorithm. This is commonly known as the SJF algorithm. So this associates with each process the length of the next CPU burst, right. So when the CPU is available, it is assigned to the process that has the smallest next CPU burst. The name itself suggests that shortest job first. So the job or the process which will require the CPU for the shortest time will be given the CPU first. Now if the next CPU burst of two processes are the same, then the queuing, the simple FCFS scheduling will be used. Now for all the algorithms, whenever there is a tie, FCFS will be used to break the tie. Now in this case, how does this work? That if we have, you know, these four processes are there, actually it is more appropriate to call this shortest job first as the shortest next CPU burst algorithm, because it does not depend on the current burst, but it depends on the length of the next CPU burst of a process, right, rather than its total length, only the length of the next burst. So if if we consider this example where we have four processes 1, 2, 3, 4, and their burst times are also given here. P1 is 6, P2 is 8 milliseconds, P3 is 7 milliseconds, and P4 is 3 milliseconds. So these are the burst times for these four processes, right. Now if again using the same Gantt chart, we will schedule these processes so that, you know, they are arranged in this particular order. P4 comes, then P1 will come, then P3 will come, and then P2 will come. So here what we are looking at is that what is the next CPU burst, which is the shortest next CPU burst. So if we look at the waiting time now, the waiting time for P4 is 0 because it has the shortest CPU burst, so it will be scheduled first. Then you will schedule the process P1 because it is the next, then P3, and finally P2. So this is the sequence. We will have P4, then we will have P1, then P3, and then P2. So what is the waiting time? The average waiting time will be 7 milliseconds. Now if you compare this with FCFS scheduling algorithm, so then the average waiting time in FCFS algorithm comes out to be 10.25 milliseconds, which is much higher than 7 milliseconds that you get using the shortest job next algorithm. Now there are pros and cons associated with every algorithm. So likewise in SJF also, it is definitely better, it is optimal and it is definitely much better than the FCFS algorithm, because it will give the minimum average waiting time for a given set of processes. We have just seen that for the same process mix, SJF gives much lesser waiting time than the other algorithm. Now moving a short process before a long one will decrease the waiting time of the short process more, then it will increase the waiting time of the long process. Therefore the average waiting time will always decrease, because whichever is the shortest job is assigned the CPU, it will use the CPU faster and move out, and the next process can be given the CPU. So the waiting time for the long process will not be more, it will be reduced, because the processes which are prior to this process are using the CPU for much shorter duration. Now the real difficulty with this algorithm is that, you know, how do you determine the length of the next CPU burst. That is for the present CPU burst is still okay, but you have to find out the duration of the next CPU request. So for long term job scheduling, say in a batch system, we can use process time limit that a user will specify when he submits the job to the system. So in this case, the users will be motivated to estimate the process time limit accurately, and if a lower value is given by the user, it means that faster response, but if it gives very low value, then it will cause a time limit exceeded error and it will require resubmission, right. So therefore, generally SJF is used very frequently in case of long term scheduling, because of the same reason that it can be estimated by the user himself, and the users are generally motivated to give the correct or the right estimate of the CPU burst time. But this algorithm is optimal for long term scheduling like batch processes. It is difficult to implement this for short term implementing or short term CPU scheduling. The short term scheduling, there is no way to know the length of the next CPU burst, right. We may not know, we may not know the length, but we are still able to predict its value, right, because there are multiple studies which have been done on how the CPU burst value can be calculated, and a lot of research has gone into this aspect, and we know that the next CPU burst will be similar in length to the previous one, right. So therefore, if you compute, if you know the CPU burst of the current process, then you would know what will be the next CPU burst for that particular process, and then you can use computation and approximation of the length of the next CPU burst. We can pick the process with the shortest predicted CPU burst. Now again, it is to be understood that this is only a prediction, this is only an approximation, but it is generally predicted in an exponential average of the measured length of the previous CPU burst. So we have a length of the previous CPU burst. Using those lengths, we will use a particular formula, we can use the equation, and we can define the exponential average, right, with the particular formula that is being created or that is being developed, and using this we will know that what will be the length of the CPU burst for the nth instruction when you know it for the n minus 1, or if you know it for the n instruction, then you can calculate the waiting time, or you can calculate the next CPU burst for the n plus 1th instruction using this particular formula. Now SJF algorithm, it can be either preemptive or non-preemptive, right. See, FCFS is only non-preemptive, but this can be preemptive as well as non-preemptive. Now the choice will actually arise when a new process arrives at the ready queue, right, while a process is still executing. So when you have a process which is taken charge of the CPU and a new process comes, so the next CPU burst of the newly arrived process is to be checked. If the next CPU burst of the new process is shorter, then what is left of the currently executing process, say the newly executed process, arrived process has the next CPU burst of 3 milliseconds, whereas the process which is executing requires only 2 milliseconds to complete, then in that case the CPU will not be preemptive, because the currently executing process requires less time. But if the currently executing process requires 4 milliseconds and the newly coming process or the newly arrived process requires 3 milliseconds, in that case definitely the CPU will be preemptive. So it will preempt only in case where the process, where the time is being saved. It will be non-preemptive if the current process will if the current process requires less time, so it will allow the current process to complete its CPU burst, right. So if you use a preemptive SJF, then you call it shortest remaining time first scheduling. Shortest remaining time first scheduling, because now we are not just looking at the length of the next CPU burst, but we are also looking at the length of the time remaining for the process which is being executed in the CPU at that moment. So, as an example for this, let us look at this process mix. So, we have these 4 processes and these are the arrival times 0 milliseconds, 1, 2 and 3 milliseconds, and the burst times are given 8, 4, 9 and 5 milliseconds respectively. So, these are the times which are actually the length of the CPU burst which is given for them. Now, if the process which arrive at the ready queue at the time, then they need to indicate the burst times also, right. So, therefore, in preemptive SJF schedule is to be implemented. So, if you look at the Gantt chart here, so you have the process P1 which comes at 0 and it finishes at 1. Then you have the process P2 and the process P2 is given the the CPU is allocated the CPU. Why the process P2 is allocated the CPU? Because process P2 has a burst time of 4, whereas when it comes process P1 requires a remaining burst time of 7. So, therefore, the CPU is preempted and it is given to process P2 and process P1 is removed from the CPU, because of the simple reason that the shortest burst time next will be given. Now, when process P2 is executing, at the time process P4 will come, and when the process P4 comes, so then the CPU is going to be allocated to the process P4, right, because after 4 milliseconds this is completed. So, now the CPU can be directly given to P4, and then after P4 executes, again the same algorithm, the same comparison will be used. Now, P1 needs this for 7 seconds, whereas P3 needs it for much larger amount of time. P3 needs it for 9 seconds. So, therefore, now the processor will be given to P1 because it requires it for shorter time, that is for 7 milliseconds. So, likewise, if you calculate the average waiting time in this case, so it will come to 6.5 milliseconds. Non-preemptive scheduling would result in an average waiting time of 7.75 milliseconds. Non-preemptive would mean that once P1 is given, it will complete, whichever is the shortest will be given first and then in that order it executes. But here what we are doing, we are not just looking at the shortest, but we are also preempting the CPU in case the next process requires the CPU for lesser time than what is left of the previous process. So, again in this case we see that preemptive is having much lesser average waiting time, almost 1.25 milliseconds lesser than the non-preemptive strategy that we are looking at, right. Now, the next algorithm is a very interesting algorithm which is a priority scheduling algorithm. Now, in this case, another attribute is to be associated with each process, which is actually a number, and that number depicts the priority of the process. Now, the CPU is allocated to the process which has the highest priority, and equal priority processes again will be scheduled in FCFS or first come first served order. Now, we have already seen that in the shortest job first algorithm, a simple priority algorithm is what is the priority there? That is the length of the next CPU burst, and it is actually the inverse. Inverse why? Because the shorter or the smaller is the length, the CPU will be assigned. The larger is the burst, the lower will be the priority. So, SJF is also a form of priority algorithm or priority scheduling, but it is only one priority that we are using, that is the inverse of the CPU burst time. So, in priority algorithm we will give the priorities in the form of numbers, right. We will be looking at the priority algorithm in more detail in the forthcoming lecture, but it is very important to understand that in shortest job first algorithm is also a simple priority algorithm where the basis of the priority is the inverse of the CPU burst time. So friends, that will be all for this lecture. We will be continuing with priority scheduling in the forthcoming lectures. Till then, please keep watching CEC. Thank you.